Good afternoon, students. Hope all the students of X1 and X2 are here. 1, 2, 3, 4 is not here. 4. Then 5, 6, 7 is absent. 8, 9 is absent. 10, 11, 12, 13, 14, 15 is absent. 16 is present. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 are absent. 24, 26, 27, 28, 29, 30, 31 is absent. 32, 33 is absent. 34, 35, 36, 37, 38, 39, 40, 40 is absent. 41, 42, 40 and 42 are absent. Then 44 to 47 are absent. 48 is present. Now who else joined now? 43 has joined. 41,
29, ma'am.
29 has joined, right? Okay. Yeah. Okay. We'll see who else is joining. Okay. So because this is I told 3 o'clock I'll take the class. That is why like now I think I have given you the experiment on uh, ion exchange capacity, right? Are you all having the experiment for determination of ion exchange capacity of a cation exchange resin? Am I audible to all of you?
Yes, ma'am.
Okay. So if I'm audible, I think I have given you the PDF in the group for ion exchange capacity determination. Now the second experiment of your second, like the second part after sessional part is experiment on adsorption of acetic acid on activated charcoal. Okay. Now this experiment is verify Freundlich adsorption isotherm. So you would need 5 conical flasks, 5 burette stand, pipette, measuring cylinder, funnel, filter paper, and so on. This is the what is an adsorbent, what is an adsorbate. We have already discussed. So here we see according to Freundlich adsorption isotherm, which is an empirical equation without any theoretical backing, x by m, which is x is the amount of adsorbate adsorbed on m gram of adsorbent is equal to k into c raised to 1 by n. So K and N are constant at given temperature, and the test for Freundlich adsorption isotherm or the linearized form is this is your ordinate, and log C will be on your abscissa, that is x-axis. Intercept on y-axis is the log K value, and 1 by N is the another constant, which is the slope of the curve. Okay, so you are supposed to prepare these concentrations. So first of all, a stock solution of 1 molar acetic acid is prepared, and from this stock solution then you prepare these serial dilutions. So if you take 100 ml of 1 molar acetic acid and add 100 ml of water to it, you get a solution which is zero point 0.5 molar of acetic acid. Now from this 200 ml solution of 0.5 molar acetic acid, you again take 100 ml and add 100 ml of water, so you get 0.25 and so on. Now, here is an observation table. Now, the experiment has to be performed in a group of 2, and one student will like the charcoal is given. 1 gram charcoal packet is given. Now, this table is important for all of you. Now, what is done? Like I think I have told you that day that five conical flasks are taken in which 1 gram charcoal is added, and to each conical flask this is the concentration of acetic acid which is given. So you add 50 ml of this concentration acetic acid to each conical flask labeled as 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And then one student will keep swirling or shaking this flask, that is acetic acid in charcoal or charcoal in acetic acid, and the other student will first try to find out the strength of acetic acid provided to you. So for this reason, you take first of all zero point 0.1 normal NaOH. Okay. Now this NaOH is filled in the burette, and the initial solution of acetic acid, which is provided to you 5 beakers. Okay, 5 beakers will be provided to you, so that from that beaker you collect 10 ml of acetic acid, transfer it into a conical flask. Okay, so pipette out 10 ml and transfer it to a conical flask, and to that you add phenolphthalein indicator and you titrate with NaOH solution from the burette. So NaOH solution is filled in the burette and 10 ml of the first concentration is taken. Now your NaOH is 0.1 normal and acetic acid is 0.5 molar. Okay, this is zero point 0.1 molar. For NaOH, molar normal is same because it is univalent. So, 0.1 molar NaOH versus 10 ml of first solution. So, you perform 2-3 titration using phenolphthalein indicator. The constant burette reading is written here as 48 ml. Then the second one is the next concentration. The volume required is 24 ml. Then the next. So this is the observation before adsorption. That is acetic acid initially provided to you. 10 ml is acetic acid is titrated with NaOH. Now what is done? 50 ml of acetic acid was put in 1 gram of charcoal. This is 1 gram charcoal. You are putting 50 ml into it. So when you are titrating after 1 hour of shaking, so one student keeps shaking this. So after 1 hour of shaking, you have to filter it and collect the filtrate. Now you take out 10 ml from the filtrate and perform again titration with NaOH. So these are the readings for various dilutions of acetic acid. Now, here you are supposed to find out what is X by M, that is the quantity of acetic acid adsorbed per gram of charcoal. M is 1. 1 gram charcoal is taken in every conical flask. So, what is X we have to find out. Now, to calculate this X by M, this formula is used. Now here for ease of titration and all 10 ml is used, but actually 1 gram acetic acid, 1 gram charcoal is present in 50 ml of acetic acid each concentration. So whatever be the concentration, we write here, this is V1 for 10 ml, this is V2 for 10 ml after adsorption. So this is before adsorption, this is after adsorption. So V1 minus V2 is the quantity adsorbed, the quantity of acetic acid adsorbed into 5, because if you take 50 ml instead of 10 ml, it will be into 5. So the difference of V1 minus V2 into 5 will be the acetic acid adsorbed by this 1 gram of charcoal. So 5 into V1 minus V2 into the molarity of NaOH, that is 0.1, okay, into 60, that is the um, molecular weight of acetic acid, into 1000. Now 1000 is written to get it in milligrams of acetic acid instead of grams of acetic acid. This 60 into 1000 will give milligrams instead of grams of acetic acid upon, like you took 1 gram charcoal, so 1 is written here, 1 gram charcoal into 1000. Okay, so into 1000. This is this is X by M is equal to the quantity of acetic acid adsorbed into zero point 0.1 into 60 into 1000 upon 1 by 1000. So 1 gram. So this 1000 should not be there. Are you getting? If you are writing G of,
Ma'am,
yes,
ma'am, every time V1 will be greater than V2, na?
V1 will be greater than V2 because this is before adsorption, and after you put 50 ml of acetic acid in 1 gram charcoal and shake it for 1 hour, your V2 will be lesser because some part of it has been adsorbed on the surface of charcoal, activated charcoal. So V2 will be lesser
Okay, ma'am.
than V1. Okay, so X by M comes out to be 5 into V1 minus V2 into the molarity of NaOH into the into 60. Now, if you multiply this by 60 upon 1 gram charcoal, for 1 gram charcoal, it is the quantity. If you just multiply it by 60, that means grams of acetic acid per gram of charcoal. Okay, so if you multiply it by 1000, this 1000 will give you milligrams of acetic acid adsorbed per gram of charcoal. So that's why I'm writing 1 gram of charcoal. Okay, then what is the equilibrium concentration? That also we have to find out. Now this is the initial concentration provided by the attendant. Now this, when you perform titration, you came to know that you require this much quantity NaOH, say it is already known standard solution given to you. So if this is the standard solution, you are performing using 10 ml. So CE for each solution will be determined by putting, like for the first value, CE will be equal to what? 0.1 into V2 is 44.8. That is after adsorption, whatever is the volume, that will be your this thing, divided by 10 ml was taken for titration. Now this is there. Now this will be equal to equivalents per liter. So what all answer you are getting? A answer into 1000 will give you milli equivalents per liter. So why this 1000 is multiplied here also, and in X by M also we are multiplying it by 1000, because if you don't multiply it by 1000, if the decimal values are there, no, these values will be negative. Log of X by M and log of CE, that will be negative. और फिर negative आने से what happens when you are plotting log X by M versus log CE, then your graph goes into the second or the third quadrant. Okay, so because we want it to come in this, so for every solution you have to calculate this X by M as well as CE, the equilibrium concentration. Now here the equilibrium concentration will be 0.1 into 20.5 divided by 10 into 1000. Okay, so this will be your equilibrium concentration. We try to increase this particular thing. Okay, log C, log X by M. So this is how you will use this X by M formula here in each of this, and try to find out what is the, okay, so this is your X by M. That will be excess milligrams of acetic acid per gram of charcoal. Okay, and this will come out to be in positive value, not in fraction. Fractional value रहने से log becomes difficult. So M is 1 gram, equivalent weight of acetic acid is 60, normality of NaOH is 0.1 normal. V1 minus V2 indicates acetic acid adsorbed. The factor 5 comes in X by M calculation because 10 ml is taken for titration, whereas set was made of 50 ml in 1 gram charcoal. So a multiplication factor of 1000 is used in both cases to have positive log X by M and log CE values. Okay, so once you get this, you have to plot two graphs. Okay, so two graphs you will plot, and that will be, one will be X by M versus CE. Okay, X by M versus CE, and the other one will be log X by M versus log CE. So two graph you have to plot. Okay, interpret the graphical plot as if a straight line is obtained. Not only this, you should plot X by M versus CE and log X by M versus log CE. So X by M versus CE will be something like it will be X by M. Like if you plot X by M versus CE, okay, so the red one is like this, you will get it like this. Do you have an eraser here? Eraser. Okay. Okay, then this is what you will get. Like if you are getting it like this, log X by M versus log C, maybe you will be getting a straight line like this, like some point should be like draw a line having half of the points above and half below, or try to put your scale in such a way that 3 points are on the scale or on the line, and rest of them, one is above and one is below. Such kind of a plot should be plotted. Then extrapolate this particular graph on your y-axis. So this value becomes log k. Okay, so if you get this log k, take an anti-log of this k. So you get an anti-log of k, and this value slope y2 minus y1 by x2 minus x1, okay, will be 1 by n, which is termed as slope. Okay, so therefore n will be equal to, so the reciprocal of that, you will determine n value. Then you write your result as that is what is written here. So first is the plot of X by M, and second one is plot of log X by M versus log CE. So one graph will be this red one, X by M versus CE, and the second one will be log X by M versus log CE. Okay, so that will give you values of the constant k and n. So you have to report in the result. You will write from the from the adsorption experiment of acetic acid on charcoal, the Freundlich adsorption isotherm was verified or studied, and the values of constant K and N were found to be, okay, were found to be, जो भी आपका value यहाँ पे you will be getting K and N values, you will write here. The value of K and N were found to be, the value of constants K and N were found to be dash and dash. Okay, so this is how you will report your result. Things are clear? No more slide is there. Okay. So this is all regarding the adsorption isotherm, Cronlich adsorption isotherm. Okay. So now the next experiment is colorimetric determination or spectrophotometric determination, because spectrophotometric determination of cobalt is there, and experiment on bomb colorimeter is there. Okay, I'll open it. Okay, so I'll be giving you the PDF of this particular experiment, and things are clear for you for this particular experiment. What you have to calculate? Yeah,
Yes,
anyone?
ma'am.
The values of K and N should be calculated. Okay, as I have told you, from the like you will be plotting two graphs, one of x by m versus c and another of log x by m versus log c. Okay, so the colorimetric experiment and bomb colorimeter, you can try to see here and again see. Okay, then I'll try again. Might be in pen drive. Okay, the next experiment is verification of Beers-Lambert's law. So the aim is to verify Beers-Lambert's law. Now, this is an experiment which is coming from the this experiment is from the topic interaction of radiation with matter. It's an important topic. Okay. Am I audible to all of you?
Yes, ma'am.
Yes,
ma'am.
how you are?
Yes, ma'am.
Okay. Now the basic concept is here you are having like a colored solution is there. Now, what we know that if any substance or any compound, any chemical or in nature, a flower or anything is appearing if it is blue in color, like this thing appears blue in color, that means it is absorbing which light and reflecting which light. You have the visible light spectrum is VIV, GY, OR, VIBGYOR. Okay, so the electromagnetic spectrum comprises of light, not light, radiations of a very high energy, that is gamma radiation, then your X rays, then still lower energy is UV light, ultraviolet light. Then after ultraviolet, the visible part is there. So visible light has the wavelength range of 400 to 800 nanometers. Then after visible light, then you have infrared radiation, still higher wavelength and lesser energy. Then still lesser energy will be in your microwaves. So these microwaves are used for number of application like your satellite communication and all. And also the next that is radio frequency radiation. So among this, in this electromagnetic spectrum, the visible part of light is 400 to 800 nanometer, and this visible light, when is incident on any solution or any compound, it will be absorbing, like if it is VIBGYOR. So if this is appearing blue in color, that means it is absorbing the complementary color and reflecting the blue light. So this is having a lambda max or wavelength at which it strongly absorbs in the red region. Okay, so it absorbs all other radiation and more prominently the redder region, red radiations, and is reflecting blue light, and that's why it is appearing blue in color. Now this solution appears red in color. This is the stock solution you can see in the volumetric class. Now this is appearing red in color because the visible light which is incident on this uh, it is absorbing more in the VIB indigo part, or the complementary, like it is reflecting the red light but is absorbing more strongly in the 400-500 nanometer range, whereas a blue solution will be absorbing more in the red region, that is in 700 to 800 or 600 to 700 region, like that. Okay, so this is how your different colored compounds, or different, a flower is yellow in color. Yellow colored flower is reflecting yellow light, that is why it appears yellow in color, and it absorbs more strongly the opposite light. Okay, so that is regarding why and how you are able to find or detect the colors. Now, if you are having colored solutions or colored compounds you can make, then you can determine qualitatively and quantitatively these particular substance. So for this, there is a law called as Beers-Lambert's law. Now, according to Beers-Lambert's law, when a monochromatic beam of light is incident on a colored solution, the intensity of the quantity of light absorbed by the colored solution will depend on the intensity of light which is incident on it. For example, if you are having a red colored solution, VIBGYOR, so it will reflect most of the red light, but it will absorb more prominently in the blue part of radiation. So what is seen, that unless there is that particular radiation, this solution will not be absorbing light. So, according to Beers-Lambert's law, the intensity of light incident on the solution, as well as the concentration of this absorbing medium, um, will govern or will decide what is the quantity of light absorbed. Now, if some light is absorbed, the beam of light which is coming out of it, which is termed as transmitted light. So, the transmitted light will be lesser. So, when a beam of monochromatic light is incident on a colored solution, then there can be either scattering, or there can be absorption, which is shown by a round here. There can be reflection, okay, and there can be transmittance. So the transmitted light is one which we are able to measure. So using this particular concept, that every solution, depending on its concentration, will absorb a specific wavelength light, we can go for quantitative determination. What is the quantity of analyte present in it? Okay, so here it is shown intensity of incident light. This is the intensity of transmitted light. So if intensity of incident light is I0, then IT, we can write IT as the intensity of transmitted light. This is the path length. Path length means this is the cuvette which holds the sample. So this is the path length during while passing through this path length of 1 centimeter, that is length, path length L. We find that at each layer absorption goes on, and the transmitted light is having lesser intensity. So the same thing was first of all found by Beers and Lambert. According to Beers and Lambert's law, the decrease in intensity of light with the thickness of absorbing medium at any point is directly proportional to the intensity of light. Okay, that particular light which is incident. Now, it is not necessarily like if some solution which absorbs strongly at say 500 nanometers, if you irradiate such a sample with a 700 nanometer light, you will say that there is no absorption at all. So it depends on the intensity of incident light beam, as well as the concentration of the absorbing medium. So simultaneously we can say that more the concentration of absorbing medium, more will be the quantity of light absorbed and less will be the transmittance. So from this we can write transmittance is equal to T, which is equal to IT by I0. So percentage transmittance is percentage T by 100. According to Lambert, when a monochromatic light passes through an absorbing medium at right angles to the plane of surface of the solution, the rate of decrease in the intensity with thickness of the medium is proportional to the intensity of incident light. In other words, the intensity of transmitted light decreases exponentially as the thickness of medium increases arithmetically. So Lambert, what he did, he took one cell of 1 centimeter path length, another cell of 2 centimeters path length, another cell of 3 centimeter path length, and he tried to study what is the quantity of emergent light. So the emergent beam of light had lesser intensity if the path length was increased. So that was what was determined by Lambert. So Lambert could correlate that with increase in the intensity of transmitted light decreased, okay, exponentially, or the intensity of absorption increased with the thickness of absorbing medium, or transmitted decreased with the thickness of medium. Okay. So here is the derivation: minus di by dB is equal to Ki, where K is the proportionality constant, B is thickness of medium, but B, instead of B we generally write T, dt. Okay, thickness as T, like we are, okay, if it is B written here, we will call B as the thickness of medium. I is the intensity of incident monochromatic light of wavelength lambda. Now integrating the equation and putting I is equal to I0 when B is equal to 0, In I naught by IT is equal to KB. So I naught is the intensity of incident light falling on the thickness B. IT is the intensity of transmitted light, and K is the absorption coefficient for the given wavelength and medium. So converting from natural log to the log to the base 10, IT is equal to I0 10 to the power minus KB. So finally, your equation, when when it was Lambert, it said that it is the thickness, and Beer said that with increase in the concentration, intensity of transmitted light decreases exponentially. So instead of thickness, now there was the term C. So IT is equal to I0 exponential minus K prime C. So C is the constant concentration, and K prime is the proportionality constant. So this K prime and the K here, these two constants, if you merge them together, IT and I naught are the intensity of transmitted light. This is the intensity of incident light. Then you can say that your log of I0 by IT, like IT is equal to I naught 10 to the power, like this is epsilon CB. Okay, so CB or T. So K and K prime are epsilon. Epsilon is the molar extension coefficient. So we can write the final expression of Beer's-Lambert's law together, where both C and B, because Lambert said that with the increase in the thickness of medium B, and Beer said that it is the concentration. If you go on increasing the concentration, the intensity of absorption increases and the transmitted light intensity decreases exponentially. So finally, the Beer's-Lambert's law put together appears this way: log of I0 by IT is equal to epsilon CB, where B is the thickness, C is the concentration, and epsilon is the molar extension coefficient, a constant dependent upon the wavelength of incident radiation and the nature of absorbing material. Okay, and the concentration is expressed in gram moles per liter. Okay, so based on this Log I0 by IT is termed as the absorbance. So absorbance is equal to epsilon BC. So A is the absorbance or optical density. Epsilon is the molar extension coefficient, which is like a constant for one particular type of analyte or colored solution. C is the concentration of the drug or any analyte, whatever you are taking. Now here we are taking cobalt chloride. Then B is the path length. Okay, so that may be mostly it is in 1 centimeter, path length is 1 centimeter. So absorbance is equal to epsilon CB. Absorptivity if concentration is expressed in grams per liter, if it is not gram mole per liter. Okay, so here we find absorbance is equal to log to the base 10. I0 by IT should be here, that is the transmitted light intensity, epsilon C into 1 because the path length is always 1 centimeter, so it is written 1 here. So this is the absorbance value, light intensity absorbance, and these are the lambda or wavelength lambda. So mostly in visible region it is recorded from 400 to 800 nanometers. So when you record, say, keeping the instrument at 400, 420, 440, 460, 480, 45, 500, 520. So at each wavelength, you determine what is the absorbance value and then you plot them. So you get somewhere you get a peak. Now the peak where you are getting highest absorbance is termed as wavelength of maximum absorption. So that is denoted as lambda max. So this becomes the lambda max. So for each solution, you are this value wavelength at which maximum absorption is shown will be varying or will be different. And for like yellow, green, blue, red solution, this lambda max value will be different. And then once you know what is the lambda max value, then your determination can be done at that lambda max value. So here we see some of the formulas to calculate some numericals. So T is equal to the transmittance is equal to IT by I0. Percentage transmittance is equal to 100T. Then absorbance A is equal to log to the base 10 I0 by IT. So this can be written as I0 by IT can be written as log to the base 10 1 by T or minus log 10T. And then absorbance can be written as log 10 log to the base 10 100 by percentage T or 100 log of 100 is 2, so absorbance is equal to 2 minus log T. Okay, log to the base 10. This 10 should be like put into subscript. Okay, this is log to the base 10T. Okay, so 2 minus log T will be the if you don't have the values, then you can calculate from transmittance scale. What you determine from the instrument, you can calculate absorbance also using this formula. So it is seen that for a solution, colored solution, and if you prepare a serial dilution, different concentration solution, just now I have shown you a photograph, so you can determine uh, the absorbance of each dilution and plot a calibration curve. So a straight line passing through origin will verify Beer's-Lambert's law. So you should write in result that a straight line passing through origin verifies the Beer's-Lambert's law. Then according to Beer's-Lambert's law, whatever be the concentration, even at higher concentration, it should show the linear increase, but it is not so. At higher concentration, Beer's-Lambert's law is not valid. Many a times it show a negative deviation, some of the time it shows positive deviation. At higher concentration, it does not remain ideal. Okay, the reason for this deviation is when the concentration is more, the solute particles are very close to each other, and the electron distribution around one molecule affects the electronic distribution of another molecule, and that is how many a times the molecules tend to dimerize or some uh, uh, isomerization takes place, and the refractive index of the substance changes, and because of which it shows deviation. Okay, this is a spectrophotometer. With this, we will come in. We will be dealing with in the interaction of radiation matter. Okay, so this is a spectrophotometer, and like you here you can see certain commands are there. When you open this spectrophotometer, there are 1, 2, 3, and 4 slots. You can keep your cuvettes here. Now every slot is open from this side and this side. So the light beam will be coming from this side and will be passing through here. The ray diagram should have been shown properly. So in this spectrophotometer, these are two cuvettes. Now these cuvettes are made up of quartz. The quartz cuvette, like the surface of this quartz will not reflect any light, and they are almost similar. Now a stock solution of cobalt chloride is prepared, and from this 5 ml, 10 ml, 15, 20, 25 and 30 ml is taken. No, this one is unknown I think, and the 5 sequential dilutions are prepared by taking from the stock solution known quantity and then making up the volume by adding distilled water to 100 ml. So now because the stock solution concentration is known, you are knowing the concentration of each solution for cobalt chloride. Now initially you first take the blank reading by taking distilled water in one of them, and then whatever is the blank reading that you have to just note it down, and first of all find out what is the lambda max. So you take the stock solution in one cuvette, distilled water in another, and go on noting the absorbance for the stock solution at different wavelength. Keep on changing the wavelength, 10 nanometers wavelength you can change, start from 400 or 430 nanometers and go on, and just note down the absorbance. Now that those values are there, then you plot this type of curve, this absorbance versus wavelength. So with the absorbance versus wavelength will be something like this. So where you are getting the peak becomes the lambda max. So this is the first part of the experiment. Then once you get the lambda max, then what you are supposed to do is you have to wash the cuvette nicely, thoroughly. The cuvette हाथ में पकड़ के like should be held in hand. It is like just a square shaped like a cuboidal tube. Okay. So these are the readings. So one by one, like we start from the lower dilution. So once you get the lambda max, then you have to maintain in this instrument, you have to put that wavelength here, mention that wavelength. So the readings are taken at that wavelength. And then you take the lowest concentration or the most dilute solution first in the cuvette and note the absorbance. Then you discard it into the sink and then take the second one, rinse the cuvette and take the second solution. Similarly, after that, you take the third one, fourth, fifth. So this is how you will get. These are the absorbance at different wavelengths, and the readings are taken from 400 to 550 nanometers, and this becomes the region where you are getting maximum absorption. So this becomes your lambda max. Once you determine lambda max, then we go for determining the unknown concentration. For unknown concentration, you need to plot a calibration curve. So calibration curve is plotted by noting the absorbance for different concentration solutions. So what is shown here as 1, 2, 3, 4, 5, 6. The concentration is written here 0.28 milligrams of cobalt per ml, 0.56 milligrams of cobalt per ml, 1.4 milligrams of cobalt per ml. I think they have interchanged it. This should have been here and this should have been here. This is the third solution. 0.8544 milligrams per liter should have been the third solution, because this is 0.85 and this is 1.4. Okay, and this is number 5 solution of 1.708. Okay, so when you take those solutions into it, into your cuvette, the absorbance is found to be these values. For this first solution, 0.28 milligrams per ml, the absorbance was 0.05. For this, it is 0.07. For the next two, three, it was like this. Okay, so that's all. So you need to plot a calibration curve like this. Okay, so from these readings, this reading, you will plot a calibration curve. The calibration curve will be, this is absorbance versus concentration. Now in this case, you have here 0.28, that is milligrams of cobalt per ml. This is the first concentration, right? The second will be the next one, third, fourth, fifth, and sixth. So what all concentrations are given, and just try to plot the concentration against the concentration. Try to put your absorbance value. If you are getting something like this, try to put a straight line passing through origin. Okay, and then you have some unknown. So when you have unknown, the absorbance of unknown is given to you. So this unknown absorbance, put a dotted line to this particular straight line, and where it is intersecting, put a dotted line in the lower part. And if you get it here, this will be your unknown concentration. So that is how you this is a relative technique in which you are comparing the result of your determination with the standard or the reference one. So this was the unknown solution given to you, and this unknown had an absorbance of this value. That is why they have written it in between. Rather, this should be written at the bottom, that this is the unknown and the unknown has this absorbance. So from the absorbance value, from this value, you go to this particular, this graph. This is termed as calibration curve. Okay, so with this, your experiment for Beers-Lambert's law is over. What you will be writing is, so these are the two observation tables, and from these two observation tables, you are supposed to plot first graph of uh, absorbance versus wavelength, which will give you lambda max, and then you are supposed to plot the calibration curve using the second observation table, and the calibration curve will be absorbance versus concentration. Things are clear?
Yes, ma'am. Yes.
Okay, so like we have completed ion exchange capacity, we have completed adsorption, verified Freundlich adsorption isotherm, and we have completed today Beers-Lambert's law. Now this being and what you say, common slides for all the BTech students. Actually, there should be proper procedure written, and rest of the instructions should be written. Um, like the common PPT is prepared by different faculty members. That's why the explanation for this is not there. But I think what I explained to you is clear. If you want, I can again, because when we will discuss the theory part of it, again we will be discussing all those things. Clear? Okay. So you can write this experiment in your file. I'll give you the PDF of this. Okay. So here we stop today.
Thank you, ma'am.
Thank you, ma'am.
Ma'am.